we're going to have a brief discussion with a panel of PIs, and so one of the great pleasures of working on this project is to have such a remarkable group of co-conspirators in the formation and execution of the Black Hole Project, not only among my colleagues here, who I'll introduce in a moment, I think all of you know them, but also the visitors, fellows, faculty affiliates, postdocs, graduate students who make this place so wonderful to work in. So, you know Avi, he's spoken already. Avi does a wide variety of projects around black holes, astrophysics more generally. He's somebody able to move quickly as developments unfold in the field and has contributed to a huge variety of different aspects of black hole physics and astronomy. Andy Strominger is a theoretical physicist whose work brings together these fundamental questions around the information paradox in his collaboration with Hawking and Malcolm Perry, as you've seen in the film. He asks important questions that really press the limits of our understanding about physics and general relativity. Ramesh Narayan is an expert on the accretion disk, all of those materials that float around the black hole and some of which fall in, and they give us so much of our signal about what these otherwise invisible objects are. And his remarkable group has contributed a huge amount to our figuring out how we can actually transform these invisible objects, black holes, into something that we can observe. Shep Doeleman is our observer. He's head or director of the Event Horizon Telescope and managed to herd the proverbial cats in these observatories all over the world. It's a remarkable accomplishment of coordination, both scientifically and in personnel. Not a trivial matter. This expedition to understand and make an image of the black hole for the first time is well on its way with a remarkable set of observations that we hope will yield the first images in the coming months. And Xingtong Yao, at the end of the table, is a mathematician whose work has contributed in many ways to our understanding of string theory and black holes, geometry. He crosses back and forth across the boundary of physics, applied mathematics, geometry in so many ways, and adds a tremendous dimension, along with his students, to our understanding of black holes and their mathematical dimension. So I thought it might be useful for us to just take a moment, and if I could ask my colleagues to just say a few words about what the combination of disciplines that we've assembled here has meant for them. And that is to say, we're only, 8-9 months into this project, but already we've begun to see a lot of collaborative work, and I thought maybe go down the table and say a few words about how you think it's begun to come together intellectually, and then have a chance for people to ask questions or comments and have a discussion in the full room.
So to me, the most thrilling experience was the ability to meet people in the corridor that I usually do not interact with. And as one example, I'd mentioned the paper that we wrote with the postdoc Paul Chesler about constraining modified theories of gravity, theories that are alternative to Einstein's theory of gravity, ruling out many of them based on gravitational waves that were detected by LIGO from a pair of black holes that merge at the edge of the universe. And so that's just one example for a collaborative project that I would never do unless I was affiliated with the Black Hole Initiative. And to me, that's a thrill. And of course, listening to philosophers for me is closing a circle in my personal life, because when I was young, a teenager, I was mostly interested in philosophy. The reason I ended up in physics or in astrophysics was the result of circumstances. I had to serve in the military, and that was the path to continue intellectual work, to do physics. Philosophy was not of much interest to the military. And so it's sort of closing a circle for me that I can speak with philosophers, speak with mathematicians and physicists in the same corridor, and I'm really very excited about this and look forward to many years of collaboration.
Yeah, so I think I'll tell a little story. About 10 years ago, one of Ramesh's students, Rebecca Shafee, asked me to be on her thesis committee. And as a faculty member at Harvard, we always try to avoid being on committees, but at the same time, it's our duty to do it every once in a while. And so I agreed to be on Rebecca's committee, and I thought, this thing. And then I'm listening to her and saying, wow, this is really interesting. And maybe some of the tricks and things that I've learned from studying quantum black holes can be brought to bear on this problem. And that started, I don't know if I've ever said this, but that started, that little kind of chance interaction between physics and astronomy started what has now become a whole research program with people all over the world involved in using techniques and ideas from string theory to understand things about the kinds of black holes that we're now seeing in the sky. And so these little chance encounters, the path of a scientist is full of these, and they're absolutely crucial. And we draw in a university, we draw circles around intellectual disciplines, and we call them departments. And we bounce around in these little circles, but they're really random circles because my own interests tend to be closer either to people in the math department or the astronomy department than many of my own colleagues in physics. So what we've done at the Black Hole Initiative is we've drawn a new circle. And I think it's a very appropriate circle, which leads to a lot of interesting interactions. And I have found that, again, as a faculty member, you tend to do things that you're supposed to do rather than what you want to do. And now I'm supposed to go every week and listen to astronomers talking about black holes. Turns out to be really interesting. And so all kinds of things get, new ideas get, in really unexpected ways, I think have been percolated by this new circle that we've drawn.
Wonderful, Andy. That was great. I was excited about this PHI even before it actually came into being. And the reality has been a lot better than I had anticipated. The thing is, I always think of myself as a physicist. I've been in an astronomy department now for decades, but I always think of myself as a physicist. I've always wished that I could be with physicists and mathematicians and other disciplines other than astronomy, so that I could care about things going on. And the BHI has made that possible. We have this center. We all meet at least once a week for the colloquium. There's a whole day when we are chatting about everything, different aspects of black holes. It's just wonderful. It's just the highlight. So that's been great. What I didn't anticipate, and which has come to me as a wonderful surprise, is that I really like philosophy. Yeah, I'll be honest.
We like you too, Ramesh.
Thank you, Eric. I have a PhD like everyone else here, right? You're all doctor of philosophy. I never knew what philosophy was. I knew I was a doctor of it, of course. I didn't know what it was. I always thought it was all words and, sitting in an armchair and having deep thoughts and all that. But we have had this one semester now of philosophical discussions of black holes, led by Eric and Peter and Ned Hall. these are real practicing philosophers who come, and then the rest of us who really don't know what we're talking about, but we are all interested in black holes. And it turns out that it is not such a difficult language, at least the language that these guys speak. Eric is really a mathematician. So he comes, and that I can understand what he's talking about, but he's asking much more hard questions. This is something that probably I would never have had in this life if it hadn't been for the BHI, and if we hadn't been smart enough to invite Eric to come here. And hopefully you're going to continue coming because those sessions have been the highlight. But this, I think, is an example of how wonderful it is to have really very distinct fields come together, and when you can start talking, and you suddenly broaden. Where we are going with our philosophy discussions, I don't know, but we had several big questions that we have left unresolved. The semester is ended, unfortunately, but we should continue discussing, including as deep questions as, what does it mean for the wave function to collapse? And if the wave function can collapse, is there really an information paradox? Andy, you missed that discussion. That was amazing, yeah. So these are, we're asking really deep questions, but we're coming at it from the physics and the philosophy angle. And it's been an eye-opener. I'm really looking forward to the next 2 years and hopefully many more years beyond that.
I just want to say I'm shocked that you haven't figured out everything in philosophy.
Okay.
You made it sound like you always had a shot at it. We just figured it all out. So I share the sentiments of everyone who's spoken so far. I'm pretty siloed. I'm a little bit the odd person out. I'm the observer here. I go to mountaintops, I telescopes, I take data, and most of the people here are a little more theoretical. But I found that there are deep connections with the Event Horizon Telescope project with everyone here. So it's going down the line. Peter and I have now been up to 15,000 feet at the top of a volcano together, pondering what it means to think about reaching across 100 years with a handshake to Einstein and trying to prove or disprove or shed new light on what his theories might tell us about the boundary of the black hole, and to have that documented and to have Peter's interesting take on them and also Eric's. I found the idea of what it means to prove the existence of a black hole is quite interesting. Just because you make some measurements doesn't mean you've proven anything, right? I mean, have you seen a horizon? Are there other alternatives to a horizon? Are there exotic constructs like boson stars that could be different than black holes but mimic them? These are all very interesting and deep questions, physically but also philosophically. Now I've already published papers with Avi and with Ramesh, and now we're working with one of Andy's students, Alex, on some deep questions of lensing that the Event Horizon Telescope may be able to shed light on. And it's been just a wonderful opportunity to get together with the PIs here, but also with all the students and the postdocs, the whole community. And it's really the fabric, I think, that we've built at the BHI, which is the special sauce. Special sauce, that's my last word on it.
Well, I'm a mathematician. I'm actually a geometer, largely. So I look at the universe as part of geometry, because Einstein equation does tell geometry dominates the world. And I'm always fascinated by looking at the subjects that physicists interested in or astronomers interested in. I have been going to seminars in physics department, and now in the last year, a great deal of attendance in the black hole seminars. I think I probably only understand 10% of each seminar, but accumulate for the last 30 years when I start to go to physics seminar, it has been extremely fruitful. Mathematician does want to prove things, so it's much more slow to compare with what the physicists do or the astronomers do. They jump to conclusion in general. And many of them are good, but not all of them are good. But we appreciate what they try to do, and I think this is very important for me. In fact, the first time I contacted general relativity was in 1973, when I know very little about the subject. When a physicist general relativities come to Stanford to give a talk about general relativity. And it's basically transformed into some language in geometry. I was very fascinated by that question and started to work on it, and that's called the positive mass conjecture, questioning basically whether energy is positive so that the universe is stable. And I worked on it as a part of geometry, and it's exciting because although at the beginning it doesn't seem to have anything to do with black hole, somehow black hole, the concept black hole automatically comes in, and then start to prove something, saying that under a good physical reasoning, for example, matter is rather dense, then a black hole would exist. I still remember that it was very fascinating when I proved that after 10 years looking at the subject. If you look at a popular magazine, they always say that it's obvious. But to translate into a statement which is mathematical rigorous, that's not so easy. And proving that is also not easy. And so black hole seems to be very natural from the geometric point of view, although I know at that time when we demonstrated, we know not much about physics. So this evolves, and I can feed back to physics, and the ideas of physics come back to me, and this has been extremely fruitful. So the subject that I start to investigate has something to do with the structure, the topology of the universe. And this becomes a subject in geometry, a very important subject, studying the topology of space with positive scalar curvature. And it's still a very fascinating, important subject at this moment going on. So many of my works are actually inspired by listening to what physicists say, and also, happily, some of them has been also useful for physics. And I've been studying something called quasi-local mass in the last 5 years, and I believe some of the ideas are useful for gravitational radiation, but it takes time for physicists to accept what a mathematician would say. In general, they will say outright that you guys are talking nonsense, too abstract, no use. But I'm glad that when time goes on, when we understand better, they are willing to accept what we say also. So this has been also true in string theory. When I developed the concept of Calabi manifolds, I asked my postdocs in those days, Gary Horowitz, and also Andy was a postdoc at that time in IAS, and they all say that it's nonsense, useless. And then well, Gary said that really. And a few years later, they found it interesting and useful. So I think there's always time left, but I enjoy interacting with physicists, and the Black Hole Initiative is a very good environment for me to listen to them. I remember when I visited Caltech, I was very happy to listen to talks by astronomers and all that, and I thought it would be useful to listen to them, and the Black Hole Initiative allowed me to listen to many of these nice talks.
So thank you, colleagues, friends. I thought it might be good for us to open up the discussion.
Peter, don't you want to give your
Okay.
thoughts on how we have been doing?
So I should say that I one of the things that strikes me, having thought about this with the colleagues for at least a year before we submitted our application to the John Templeton Foundation, who's supported us and been in not only financially but also morally in this quest. And what's so striking to me is that astronomy is filled with fascinating objects. I mean, just the most, it's been the last several decades have been golden years for that discipline. But there's something about the black hole that is different from other amazing objects that have been produced. You wouldn't see the same range of concerns voiced about neutron stars, as interesting as they are, among philosophers and mathematicians, physicists, observers, and so on, in interaction with each other. There's something about black holes that activates our imagination in wondering about this membrane of the horizon, about the nature of the singularity, of what it means to think about a total collapse of matter into a pure distension of space-time, that these things are evocative objects to us and force us to think and in ways that actually cross disciplines in these many ways. It's been a pleasure to have Eric come in as a colleague in philosophy, to have a growing number of graduate students interested in the history and philosophy of black holes, we have another postdoc coming in the fall, and we have a whole range of visitors, some of whom will speak at the conference tomorrow. We've had quite a number of fascinating colloquia with philosophers speaking in interaction with physicists, mathematicians, and observers. So it's been a very successful collaboration so far, and we're just really getting going with this project. So I'm very excited about the whole enterprise and trying to think about an object that would be fascinating even if there was only one of them somewhere, that they actually seem to control the dynamics of galaxies in many ways, all the way down to the scale of the most minute aspects of microphysics is remarkable and challenges our very concept of knowledge, which is what I think makes it such an interesting object to think with for philosophers. But let me take a chance to this moment, and we have all the principal investigators here, many of the collaborators on faculty, postdocs, graduate students among you, and take this moment to see if you have thoughts or questions about where we are, where we're headed.
Anyone that would like to ask a question? Please.
So first of all, I'm an outsider. I'm at Yale, and the reason I snuck in is I didn't realize I was invited today. So. But anyway, I think what's really happening here is intellectually very, very exciting, what you guys are doing. I think what has happened in physics is that there are many, many problems, including black holes, dark matter, all these sort of frontier problems, where we're at an intellectual impasse in terms of making progress. And it's not for want of tools at this point, right? We have the best possible computing, new detectors, and lots of sophisticated ideas, and yet we've not cracked and understood these phenomena. So it's clear to me that an interdisciplinary approach, we don't quite know in what way this is going to be collaborative in terms of giving us an intellectual outcome, but it's clear that this is the process. That, talking to people who look at these different phenomena, cosmic phenomena, in completely different ways is going to be enriching. So as an outsider, sitting sort of in New Haven, watching, getting all your emails, and then being sort of fortunately invited to both the inauguration and to your first conference, I think you're doing something that's really quite remarkable and pioneering. So I think you should not force yourself to be gauged by conventional benchmarks. I hope you're not going to say, oh, how many papers are we producing? I don't think you need to use those benchmarks. I think the fact that you have these interdisciplinary colloquia, where you're managing to attract philosophers, mathematicians, and physicists to be at the same talks is exceptional. This is an exercise that has not succeeded at most other institutions. So I'm really excited and look forward to seeing what's going to come out of it. And in particular, I want to give a shout out to Shep and the Event Horizon Telescope, because I think that this activity has kind of catalyzed, in many ways, this conversation. And this is going to be the discovery of the next decade, what we're going to find about the black hole at the center of the Milky Way. This is the nearest supermassive black hole to us. There's a whole bunch of us who built our careers trying to model these black holes and so on. But I think the kind of data that we're going to get, and the kind of complexity in terms of how we're going to have to up our tools, our thinking, because of this quality of data, is going to really leapfrog us. So I think you should be patient with your metrics and not get bogged down with these usual. I think you should just be bold and not worry about the number of papers you're producing or whatever. Just, you know, should tell Ashley.
Don't complain. Please don't complain.
Yeah, because I think, yeah, you heard that, right? Loud and clear. Yeah, because I think it's really important, because I think a lot of these interdisciplinary efforts and institutions, what happens when you start fixating on metrics like that is that you don't, you actually disincentivize cross-disciplinary conversations. It's not easy to produce a paper with a collaboration between a philosopher and someone like Avi, who has like an idea a minute, right? I mean, it's a very different style of thinking about problems. So I think we should have new metrics. And the metrics can just be conversations. And I think this is what universities are for. I'll get off my political pulpit now.
But ultimately, we will be judged by our ability to organize a trip to the nearest black hole.
Well, now.
The good news is that it's a one-way trip.
Exactly. There are lots of people I would want to sign up for that trip. I don't know if I want to sign up myself.
I'd like to ask the PIs a question, and this is actually, in a way, this is quite complimentary to the remarks that were just made, because this is not about metrics. I'm honestly very curious, all of you, if in a perfect world, y'all had access to all the resources you needed, everything, you just had the best ideas, you came up with the best arguments, what is the single question that you, say, in the next 5 years, you really, really, really want to see a decisive answer to?
Well, it's clear what ending.
Yes.
Well, I mean, I think it's pretty clear. I'm pretty laser focused on trying to figure out what black hole actually looks like. You know, I mean, we're graced with this object in the center of our galaxy and also in the center of Virgo A galaxy that is large enough and massive enough that its electromagnetic signature should illuminate the predictions that Einstein made 100 years ago about the space-time around that object. And you can tell something about the horizon, you can tell something about the accretion flow, and Ramesh's research is so important here because how black holes eat and redistribute matter and energy on galactic scales tell us something about why the universe looks the way it does today on these huge scales. And understanding what things look like and how physics operates at the black hole boundary is key to not just to Einstein's theories, but also the stuff that Ramesh does and accretion flows and outflows. But that's what I'm interested in. That's the question. What does it look like?
To me, the most fascinating question is not so much related to our vantage point, what we see from a distance, but it's what really happens in the singularity, because that's clearly something we don't understand. And unfortunately, the singularity is hidden from us behind the horizon, but intellectually, that's the most fascinating place where if we were to go there and look at it, we would figure something about the unification of quantum mechanics and gravity. And so, to my string theorist colleagues, I would highly recommend developing a scheme of somehow seeing what's going on there. This is the place where we can get a glimpse at perhaps what happens at other singularities like the Big Bang.
So first of all, 5 years is too short.
I'm talking about a perfect world.
Schwarzschild found his solution in 1960. Decades later, Einstein wrote a paper, 1939, that black holes don't exist. It was 50 years before we understood the classical theory of black holes. That would be Penrose and Hawking and Carter and other people in the 60s and 70s. Then we went back to step zero, when Hawking discovered the paradoxes of quantum mechanical black holes in the 70s. And that problem we've been wrestling with for 40 years now, and we are under the impression that we've understood a lot about the problem. We're also sure we haven't solved it. And so it's not something to be, and that's important in science, that we have to look at much longer than that's why I'm giving such an extended answer to this, because I'm often asked, what can you do in the next 3-year grand cycle? That's not how we think. We're thinking about 50 years. And it's a big problem, right? When we solve this problem, I think the solution of this problem will be historically comparable to quantum mechanics or relativity, and we shouldn't be expected to produce something like that in a 5-year timescale. Now, of course, we don't know exactly we know that we don't understand black holes. That's about the only thing we're sure of. But we don't know exactly what the right question is. But my kind of best strike at what the best question is what's inside a black hole? So by definition, a mathematician, would define a black hole as that which one cannot see inside of. That even 1,000 Sheps cannot see inside a black hole.
Is it a year to measure?
Shep is not going to get us inside a black hole. It's a barrier to light, but it's not a barrier to our minds. And we are under the working hypothesis that we can try to, as far as we understand, there is no self-consistent proposal for what the laws of physics are inside a black hole. It's not that there's 5 and we need Shep to do a measurement and tell us which one is right. It's that there aren't any. And so the next question is, what is a proposal? Just give me one for a consistent description of what happens inside a black hole. 5 years is probably too short for that. It's an amazingly thorny problem. And the longer we think about it, the deeper and thornier it gets, but also the more exciting it gets. And so that would be my hope.
I've been working on black holes now for maybe a little over 20 years. From the beginning, one of my big quests was how to demonstrate that these objects that we see in astronomy, and that we all freely call black holes, how can we demonstrate that they are really black holes? And the simple definition I was starting with was a black hole is this object with a horizon, is one way in my brain, and then in the middle is a singularity. So at least the singularity is beyond reach. As Andy said, it's on the other side of the horizon. Avi also said that. But the horizon is something we can try and, even if we can't quite touch it, maybe we can somehow tell that it is there. And this I've been doing now for over the years, including one piece of work since the BHI started. We got yet another piece of evidence that the objects we have been calling black holes are really black holes. They don't have surfaces, they have horizons. It's not a proof that even a physicist would agree with it. Certainly, Yao would never consider it a proof that we have shown it, but we are getting along there. So that's, I think, a really important direction to go. But the singularities, of course, that's the real interesting question, because that is where everything breaks down, the mathematics, the physics. And we have all been told that it is on the other side of the horizon. The only way to even sample it is by falling through the horizon, in which case you won't live to tell the tale. But it turns out that relativity does not rule out so-called naked singularities. In principle, the universe could have singularities sitting by themselves without a horizon around them. It's allowed by the equations. Does the universe really do it? Who knows? But I would like to know whether this is possible. Maybe even Shep or somebody will observe signals from one of them. That would be a direct view into this infinity in the mathematics. And as I realized, Eric, in fact, from our discussions this semester, even defining a singularity apparently, I always thought singularity, if something goes to infinity about a singularity, but it's a much more thorny question than that. And people are still debating what it means. So, but I think the singularity, somehow astrophysics and physics and maths should come together and ideally get a signal from one of these things if possible, and then use it to focus down on what the hell is going on down there.
Yeah, I say singular structure of space-time is one of the most difficult questions that classical relativity has to deal with. From the point of view of mathematics, this is one of the most fascinating and most difficult problems because the equation is very nonlinear and the topology of the space-time is changing all the time. So actually, just to define what it means is already a difficult problem. And Penrose call it cosmic censorship. That's one of the most difficult and classical questions we got to answer. But it probably takes more than 5 years, as Andy said. But there are many things that I think physicists and astronomers make the assumption about is the no-pair theorem, which basically says that there's only a couple of black holes model that should be there, stationary black holes. I don't believe that's theorem, actually. If you were wrong, there will be a lot of many interesting and fascinating questions that should be answered. But on the other hand, if it's right, then it's much more work to prove it, which I think is a fascinating question in mathematics or in physics too. And because all the modeling we are doing on black holes are based on this no-pair theorem, which I think should be studied much more carefully.
I think what I'd like most to know is whether there are limits to our knowledge philosophically. In the 19th century, in Germany, there was a big debate that was thought of as the question of ignoramus, what we don't know, and ignorabimus, what we can't know. And it was seen by both the side of the scientists and by theology as an important distinction. On the science side, it said, this side of the line is ours. We can discuss what goes on in science, and that side is for somebody else. But the theologians also liked this distinction because they said exactly the same thing. Our side, this is the place where science ends, and it belongs to us. So I think an analogy to that problem in some ways exists now, and we can start to ask questions about not only can we speak about what happens past the horizon, but inside the black hole that we know, there are all these complicated other kinds of horizons, and in a spinning black hole, for example, this Cauchy horizon, where all the visible light from the past and future of the universe converges. We can have inside of that backwards time travel. Are these things something that science can speak of? Are there limits to what we can know inside the black hole? It's not enough to say clearly you can't come back, and at least that doesn't move me. I mean, if you can go past the horizon of the black hole at the center of our galaxy, of M87, that doesn't stop me from thinking it's something that could be spoken of scientifically. But then what happens once you're in? What is that? And so this relates to the question that many of my colleagues here have mentioned, but I think in a philosophical frame, it represents, in a way, the ultimate epistemological question, which is, are there limits to what we can know? And what does that mean? In what sense not know? Not because our computers aren't big enough, or it will take a casualty if somebody goes past the horizon, at least for me, that doesn't move me. I mean, it may move me because somebody can't go back, but it doesn't move me as an epistemologist. So I think there are those kinds of questions. And then there are more pragmatic sides of the epistemological question about how we detect things. What about the role of our models that are used in the detection of the Event Horizon Telescope or of LIGO? Do our expectations stop us from being surprised in certain ways because we build them in to the apparatus of our understanding, the literal apparatus of our understanding? So I think for all those reasons, I think that these are objects of quite remarkable philosophical interest, and we've only just begun to think about them. And if the philosophy and the physics, mathematics, observational astronomy can work together, I think we can avoid the great error that happened in quantum mechanics, where the sides fragmented and then laboriously had to work to come together again from the 1960s through the 1980s and 90s to make entanglement the productive site for everything from physics to technology that it is today. I'd like to invite you all to come with us to see the Black Hole Initiative next door, if you'd like. Our fearless leader, Avi, is going to guide the way. Do you want to describe the plan?
Yeah, we will simply walk out to the next building and show you. See the place. Thanks to all for coming.